Inside you, right at this very moment, there's an army of microscopic soldiers on patrol. They are the silent guardians of your health, the absolute elite special forces in the constant war against disease. Today, we're going to tell the incredible story of just one of those soldiers, the T cell.
And we're going to tackle the single most important question there is. With trillions of your own cells to defend and an almost infinite number of potential enemies to kill, how on earth does this elite soldier learn to tell the difference? Okay, let's dive right in.
So, meet our protagonist, the T lymphocyte, or just T cell for short. Now, this isn't just some foot soldier. Oh no, it's the commander that orchestrates the entire immune response, and it's the executor that eliminates threats directly. It really is the central hero of your body's defense story.
To really appreciate this cell, we have to start with the sheer scale of its mission. We're in Section 1, the body's elite force, where we're going to explore the almost impossible task this tiny soldier faces every single day.
Think of this like a mission briefing. A T cell has to distinguish every one of your own cells, what we call self, from literally anything else or non-self. And that includes viruses, bacteria, even your own cells that have turned into cancer. Then it has to coordinate the battle, kill the enemy, and this is the most critical part. It can never, ever make a mistake. Because you see, attacking healthy tissue leads to devastating autoimmune diseases like type 1 diabetes or multiple sclerosis. The stakes just could not be higher.
So, where does a soldier this elite even come from? Well, they aren't born, they are made. They are forged in a specialized boot camp, a brutal training ground that turns a raw recruit into a battle-hardened warrior. An organ you might not have thought about since high school biology, the thymus.
The journey begins way down in the bone marrow, where a generic stem cell is born. It then takes a trip through your bloodstream until it arrives at the thymus, this small organ kind of nestled right behind your breastbone. And once inside, it makes an irreversible pledge to become a T cell. There is absolutely no turning back.
And that commitment, it gets sealed by this fascinating molecular switch called Notch signaling. You can think of it like a secret handshake that can only happen between the T cell recruit and the cells of the thymus. It's an amazing system that ensures these elite soldiers can only be trained in this one specific, secure facility.
Now, every single T cell needs a unique weapon to recognize its one specific enemy. We call this its T cell receptor. The body forges these using a process that is basically a genetic slot machine. Specialized enzymes grab random segments of your DNA, they cut them, they shuffle them, they even add a few more random DNA letters just for good measure, and then they stitch it all back together. The result? A completely unique receptor, one of trillions of possibilities, capable of spotting a threat that no other T cell can see.
But here's the catch. When you generate things that randomly, most of the weapons you make are duds. Or, even worse, they're actually dangerous. The training in the thymus is so rigorous, so unbelievably selective, that up to 96% of T cell cadets don't make it out alive. They fail their final exams and are ordered to self-destruct.
This whole selection process comes down to 2 life or death exams. The goal is to find T cells that are both effective and safe. First up is positive selection. This one asks, can you even recognize our own body's communication signals? If a T cell can't bind, even weakly, to our own cells, it's useless. It fails, it dies. Then comes negative selection, which asks the opposite. Do you react too strongly? If a T cell binds too tightly, it's a potential traitor that could attack us. It also fails and is eliminated. The binding has to be, just right.
Okay, so the tiny 4% that actually graduate are now what we call naive but highly trained T cells. They leave the thymus and start patrolling the body, just waiting for their one specific target to show up. They are ready for their first encounter.
Now, to prevent an accidental war from breaking out in your body, activation is a 2-key system. It's a critical safety feature. Signal 1 happens when the T cell's unique receptor finally finds its perfect match, say a little piece of a virus or a cancer cell, being shown off by another immune cell. The key fits the lock. The target is identified.
But you know what? That's not enough. Just finding the target isn't enough to launch an attack. The T cell needs a second, totally independent confirmation. This is signal 2. It's a co-stimulatory signal that basically says, yep, we confirm this is a real threat. You have permission to engage. Without this second key, the T cell just stands down. This 2-key system is the ultimate failsafe, making sure our warriors only go to battle when the danger is real.
And once it's activated, the T cell doesn't just attack, it specializes. It's so cool. Depending on the signals it gets from the battlefield, it can become different types of soldiers. A Th1 cell is like a general, leading the fight against viruses. A Th17 cell acts like an engineer, building up barricades against bacteria. And then you've got Treg cells. They're the peacekeepers, responsible for shutting down the whole immune response once the battle is won to prevent any collateral damage.
For decades, this is all just incredible biology, stuff you read about in a textbook. But now we're moving from just observing these soldiers to actively engineering them. This is where we learn how to program our own T cells to become super soldiers in the fight against our worst diseases.
Right now, there are two main strategies. The first, called checkpoint blockade therapy, is kind of like releasing the emergency brakes on your existing T-cell army, just letting them fight harder. But CAR T therapy, which is what we're going to focus on, is even more radical. It's like taking a soldier out of the body, installing a brand new GPS and targeting system, and then setting them back in to hunt down cancer.
So how does CAR T therapy actually work? Well, doctors take a patient's own T cells right out of their body. Then, in a lab, they use genetic engineering to give them a new synthetic receptor, a chimeric antigen receptor, or CAR. This brand new receptor is designed to recognize a very specific marker on cancer cells, basically turning the T cell into a precision-guided missile. This is a total paradigm shift. We're moving from chemical drugs to living drugs.
And the level of detail here, it's just staggering. The engineers building these can even decide what kind of soldier to build. By changing just one tiny component in the CAR design, the part that gives that crucial go command, they can create two totally different types of warriors. One design creates a sprinter, a cell that attacks with a fast, powerful burst but gets exhausted pretty quickly. Another design creates a marathoner, a cell with incredible endurance that can patrol the body and kill cancer for months, or maybe even years.
So, the results? In some blood cancers like pediatric acute lymphoblastic leukemia, cancers that were once considered a death sentence, CAR T therapy has achieved remission rates of over 80%. Just think about that. We are using our own retrained immune cells to achieve cures. It's incredible.
Which brings us to a final, pretty profound thought. The T cell, which was once just a subject of study, is now becoming a programmable living drug. We've learned its language, we've figured out its training manual, and we know its rules of engagement. The question isn't if we can use our cells to cure disease anymore. The real question is, what comes next in this new era of living medicine?